And you're listening to Clemens Zauchner, who is an experienced data scientist at ITPS Services. I know him back then also from the ARM meetup where he presented, I think it was HTML table. Oh, table HTML, we still don't get this. So he has also lots of experience in R, and today he will enlighten us about Trinity Smart Alerts. So thanks for coming. Clemens, the stage is yours.
Thanks for having me. Thank you.
Is
Sure. Maybe. That works. Where was I? Well, thank you for being here after the coffee break. Today I'm going to talk about a piece of work that we did in a company. So a little bit of background. We, as a first slide? No, this is the first slide. Perfect. We've developed a tool now called Trinity, and it started off with the company having to manage data centers. Now we have 4 data centers in Vienna, and within every data center you have multiple components, different servers, different vendors, storage system, so external storage, some switches in between them. You have stuff like VMware to manage your virtual machines. You have different operating systems like AIX, which is a Unix thing, Linux, IBM, which is IBM specific stuff. And all of these vendors have their own performance monitoring software tool. However, they are not integrated, so you cannot use 2 of them together, for example. And whenever there's something going wrong within the data center, it's very hard for you to actually find out what's causing the issue, because you don't have this one common view. And this is what they started off with. They wanted to have a tool for themselves to actually manage all of that. And this is how Trinity was born. So why do alerts? I'm going to talk about alerts today. Why do alerts anyway? You always want to know as a system administrator when something goes wrong within your data center. As soon as possible, basically. You don't want to have your users call you and say, the machine is down. You want to know earlier that something is going on. And in the very first iteration with the tool, they have implemented a threshold-based alert. So for example, if the system CPU utilization is above a certain X% threshold, then you raise an alert. Which is fine for some systems. For example, if you think about a storage system that has just some maximum capacity, this might work to say, I need to do something at some point, kind of an event monitoring thing. But with these systems, the state depends on the load on the system. And for certain times, a low CPU percent, 50% might be problematic at some certain points in time. There might be an anomaly for this machine. So we wanted to actually use the data itself to learn what it means for the system to run in a normal state. And this focuses on production machines, so there's quite a regular workload, a periodic load, so it's actually very easy, more or less doable to actually predict something because there is a pattern to find. So very high level overview of what it does. We can see here there's a metric, and we want to learn what the normal behavior for this metric is. In this case, we're looking at the system CPU utilization. And we can see there's a clear pattern, a periodic pattern, there's a daily variation, and there's a weekday periodicity. So we can learn something here, basically. Now what we're trying to do is we try to learn what it means for this machine to be in a normal state. And whenever there's something going on, like, doesn't work, doesn't matter. Whenever there's something going on like this in red, there's anomalous data because we do expect the load to go down, but it doesn't. And it also works vice versa. So for example, if the machine would be, the utilization would be somewhere around here, we would also detect this is not what we expect for this particular machine at this point in time. So we can raise an alert. Now, in terms of the very high level architecture, what we have in the back, there's this tool, we have some users working with the tool through a web interface, through a GUI, and within that GUI they can see the visualizations of the different metrics, as well as various servers and systems. And in the back end, we have databases that actually hold the state of the API or the system in general, and also that collect the performance metrics. And then we have created a new alerting module, the smart alerts, as we've called them, because we are very good at marketing. And the user would create an alert in the system, in the GUI, and then the tool itself would send a request to the alerting module, and the module would do its magic, create an alert, make sure that the new model is trained, make sure that the inference process starts, and then sends back the result of the inference to the API of the tool, and it then can visualize alerts or the system state. Now, what have I learned? We started this endeavor a couple of years ago, and the first step was actually, we had the system, the tool, and then we came as a data science team to this company, and we were thinking together, how can we use data science within the tool? And we did a workshop. Now, when you try to find a new use case, you always want to answer these guiding questions. You want to know what is useful, because if it's not useful, if it's not a feature that someone will use, why bother? We need to have impact. It should also be a feasible problem to do. On the one hand side, in terms of the process, the tool should be integratable, and also it should be doable from an analysis perspective. Because if you need 5 years of research time, you will not have a proper return on investment there. And this leads me to the next bullet point. You need to think about the business case. How much do you need to invest, roughly, and how much can it potentially bring? And you also need to look at the data that you have available, because with data science without data, you're lost. And starting by collecting data is probably not a low-hanging fruit. We sat together with a bunch of people. It's not just one person thinking aloud. It takes expertise from various fields. You need to have business subject matter experts, they call them business subject matter experts. They understand the domain. They are the ones who actually use the tool, probably. They are the ones who come up with the ideas, because they work with the tool themselves. They also understand the business model behind it, and they can also assess the impact a project can have. And you also need subject matter experts in all of the processes around it, that understand the features of the tools, how they work, how they're implemented, and all these kinds of things. And you need to have people who understand the data that is collected within, in this case, the tool, who understand what database it is, how it's accessed, what tables there are, what they mean, what the fields are, how information is organized, basically. And then you have the data scientists who can actually help to inspire use case ideas and to make sure that the ideas are feasible and to vet the ideas in a way. Now, what did I learn there? In order to come up with ideas that can be solved by data science, you need to have some degree of understanding of what kind of problem can actually be solved using those methods. So all of these subject matter experts that are experts in different fields need to at least have a broad understanding of what kind of problem can actually be solved. However, these experts are experts in their respective fields, and they are in the workshop to contribute in their respective fields. And they should not be thinking about the feasibility or how would I implement such an algorithm to solve that problem. And you need to be very careful, and especially when you have a technical audience, that they don't think about implementation of their idea before actually the thought has ended. And this was one of the issues that we had, because there were very technical people who programmed themselves, and they were always thinking about how could I implement that? And you need to be very careful that this doesn't happen. They should contribute the ideas and let someone else bring in their expertise. So, first learning. Now the next one is kind of cliche, a picture is worth 1,000 words. What do I mean? Usually, whenever you have an idea and you say, yeah, okay, we're going to try that, you start to come up with some kind of prototype. And within the prototyping phase, whatever you might want to call it, you trial as many approaches as possible and try to find the best one, the one that solves the problem best. However, if someone who is supposed to use a feature at the end doesn't understand what the solution looks like that you come up with, they are probably not going to trust it. Now, even if the algorithm works perfectly, they might still not use it. They say, I have no idea what's happening. This is some kind of black box. I do not understand it. I do not trust it. I will not use it. So you need to make sure that all your results are actually understandable. You can use a multitude of techniques. What I think is very helpful is if you think about how a solution would look like in, for example, in this case, we have an existing tool, in this tool. And what we sometimes do is to just draw an UI, even if it's just in PowerPoint. Grab a screenshot of the existing tool and then white out whatever you don't want to show and just add your own thing to it. It's just a mock-up, it's not the real thing, but it helps. It makes an approach more real, more tangible in a way for people. It's not an abstract idea anymore, it's concrete. And you should also think about metrics and choosing metrics, because you might choose metrics that are very meaningful to you because you have worked with them, so you understand them, but they might not be understandable for anyone else. And you should always aim to find metrics that the subject matter experts that are going to use the tool are going to understand, something that relates to them, which is a hard task and it's very domain specific, but if you can manage that, where someone really understands what this metric means in terms of model performance, but also in terms of the actual process that exists already, that really helps. Next learning. You need to find a good stopping condition for prototyping. Oops, that was too fast. We've already heard today that you should build some kind of pipeline whenever you do something, and to have a benchmark model at the very first, the very simplest implementation that would solve your problem. That's your benchmark. It's very easy to do. You don't need much computing power, just quick and dirty. This is the most basic thing. It solves the problem. This is my benchmark. And from there, you trial fancier approaches, just different things, but you always test it against the benchmark. And you need to make sure that you stop whenever you see there's not much progress anymore, why bother to actually go on? And in this case, we actually implemented the baseline model. This was by far the best solution. This week one, we had the baseline, then we iterated over it, and so there's not much to be had from any other model. It just increases the complexity of managing it. So we just stuck with the very basic thing to do. So sometimes the best approach. The next one is something that I really learned in this project, that all these DevOps, I call them DevOps principles, you can call them whatever you want, are your friend. We have chosen to use containers to ship the smart alerts. I had no idea about containers when I started. I mean, I've seen them before, but I've never worked with them. I wasn't able to create a Docker file or do a Docker compose, Docker run stuff. I had no idea what this was, but I had to learn it. And it's a great way now. I'm a bit of an evangelist for containers and stuff like that. And it was a lot of fun for me to work on that. And now all of the software actually is shipped in containers. But all of these principles that you know from DevOps to automate things, to test things, to have unit tests, they really help. And especially testing, because it helps you to refactor code without having any fear of breaking stuff. And also, when we have multiple people in the team working on this tool, and sometimes there are weeks in between me working on it, and I have no idea what happened in the backend. But I can, whenever I change something in the code base, I can be sure that whenever I break something, I can see it in the pipeline, which is really great because it just goes red and I can look at what I broke, which is nice. And having this automated pipeline to build your images, build your software, test the software is really nice. It just runs through, does this work? Pipeline, oh yes it does, perfect. Or most probably it doesn't work, but that's for another day. The next learning is picking the right base images. I've already talked about containers. You have all the options in the world. There's so many images out there on the various registries like Docker Hub and all the others. And there are great differences between all of them. You can have the full-fledged, huge, humongous distro image, like for example your Ubuntu images or your RHEL images, and they come with a lot of tools that you would know from your Linux server or your Linux laptop, if you will. Maybe even your Unix terminal. All of these tools like curl, whatever they might be, are just baked into the image. You have them available, which is nice. Makes compiling easy, makes running stuff easy because you don't need to think about any dependencies because most of them, of the basic ones, are already there. Now, this is a security risk because obviously the more tools you have, the more vectors you have for a malicious actor to actually exploit the tools. For example, if you can use curl, you can immediately check or ping or some other of these networking tools. You can check which ports do I have access to, which IP addresses can I access on this machine. So a malicious actor might actually be able to break out of the container and start doing stuff on the host, which is never a good idea. And having too many of these tools lying around is a problem. You can go the other way, the exact opposite, just from scratch, which is explicitly empty image. And you would add some statically compiled binary to that image. For example, a Graal VM in the Java world would be an example for that. This has nothing but the application that you want to run within the image, but this is very hard to do, and it only works for certain use cases. But when you have it, it's very powerful, but probably not something that's practical, especially when you start. Then there are some smaller images, like for example your Alpine image, which is very popular. It's very small, very handy. It's very fast to add additional tools, but yeah, it's tricky to use it first because it uses Musl instead of glibc, which makes it hard to compile things sometimes. So you need to get to know how this works to actually use it, so not the best starting position either. But then there are some slim image variants like your Debian Slim or the universal base image in the RHEL world, which also has a minimal flavor. And these are nice trade-off of having enough of your known world, but taking enough out of, so it's not that much risk, it's more or less small. The next one ties in perfectly with image sizes again. It's multi-stage builds. This is in a container, if you've worked with it, you know, a container file or Docker file starts with a from statement where you specify your image, and then each run, copy, adds instruction adds a layer to your image. And you don't want to have anything other than what you actually want to ship within your image, because all of these things are risks, and you might bloat an image. So all of the binaries, for example, that you need to compile stuff, you don't want to have in the final image. And multi-stage builds help you to achieve that. You have multiple from statements, and you can have a from some image, and this is my builder image. And then in the final stage, the actual image, you would just have from the base image you want, and you copy from your building stages, and then you have all your compile tools in the previous stages, but your final image is very clean and small. So it's a very good, powerful technique. And the last learning is picking the container engine. You probably have heard of Docker. This is more or less the standard out there when it comes to containers. They also made containers really popular, but it has some drawbacks, mainly around security. It runs as a rootful daemon, and some of the defaults are a security concern. You need to do some post-install steps, and usually this doesn't happen. And Podman is a very nice daemonless alternative, which runs rootless by default. It has just some heightened security benefits, which helps to mitigate the risk of privilege escalation, as I mentioned here. But it's not an either-or. You can use both. For example, we use, in some projects, use Docker for building and Podman to run stuff. Podman also makes transitioning to Kubernetes a little easier because some of the defaults in Kubernetes or OpenShift are more like Podman. But that's the last learning, and this brings me to the summary, because I think I'm about over time already. To sum it up, to go from the initial idea to production takes a variety of skills, and you don't have one person that has it all. It's a team effort. There are so many different disciplines involved, it can't be handled by just one person. And all of this is a journey for everyone, for the developers, data scientists, whatever you might want to call them, and the subject matter experts as well. And this, you can only succeed if you actually work as a team together, pull the same string. It's about culture and all these things. And to keep a model running in production, like in a tool like this, requires some knowledge of DevOps principles. I'm self-taught in all of these, I'm not an expert, but so you can learn, it's the good news, and it's fun to learn it. Thank you very much.
So, thank you, Clemens, for your talk. Please, do you have any questions from the audience? Are there any? Yes?
Thank you very much. You talked about DevOps principles in data science. My question would be, how do you apply testing to data science applications? Because from my experience, the most tedious problems are not those where you actually break something, but you do something wrong in the algorithm, and then you only find it out when you analyze the results in detail.
Well, when I talk about testing here, I'm talking about the plumbing around the model, which can, all these little functions that you have to make sure that stuff works within the tool. I'm not an expert on how to properly do the machine learning part of testing in a way, so I don't have a good answer. But I think it's always a good idea to start with things that you can easily do, because you can never go wrong with the test. And then do as much as you can, and if there are some edge cases, some things that you can't test, you will always have those, but it's better to have some fundamental tests than to have no tests, if that helps.
Any other questions? Are there any other questions? So, again, thank you, Clemens, for your talk and for being here. Please, a big applause.